Hi all. Today in this video we are going to discuss about the synchronous counters. In the previous video we have learned the asynchronous counters, that is mode n counters, etc. Today here is synchronous counters. Okay. And the basic difference between an asynchronous and synchronous counters we have already learned in the previous video. That is, in the case of synchronous counters, all the flip-flops are triggered simultaneously by the clock input pulses. But in the case of an asynchronous counters, we have seen that the output of the first flip-flop is given as the clock input of the next flip-flop. But here, in the case of synchronous counter, we are giving a single clock pulse to all the flip-flops we are using. Hence, this counter is most faster than an asynchronous counter. Okay, and the design procedure of synchronous counters are: the first step is determine the required number of flip-flops using the relation capital N less than or equal to 2 raised to n. And then, as in the case of asynchronous counters, we are using the same relation here, that is capital N less than or equal to 2 raised to n, where n is the number of, that is modulus, and small n is the number of flip-flops. And the second step is draw the state diagram showing all the possible state. We have to draw the state diagram. Okay. Then third step, select the type of flip-flops to be used and write the excitation table. Then fourth one, obtain the minimal expression for the excitations of the flip-flops using the K-map drawn. The last one, draw the logic diagram. Okay, and this is the main 5 steps we are using for the design of synchronous counters. And first we are going to design a synchronous 3-bit up counter. Okay, it should be count up, okay, in the upward direction. Okay, so it is already given that is a 3-bit counter, hence we have to use 3 flip-flops. Okay, if we are asked to design a 4-bit up counter, we have to select 4 flip-flops. Okay, but here it is a 3-bit counter, so 3 flip-flops is needed here. And the counting sequence is like that. We know that using 3-bit we can count from 000 up to 111. Okay, total 8 counts will be there. And this is the state diagram. We are starting from 000 and 001. Next one is 010, 011, 100, 101, 110, 111, and again it will repeat from 000, 001, like that. Okay, and here for the design we are selecting JK flip-flop, and we know the excitation table of a JK flip-flop. So this is the excitation table. We must learn this excitation table for the further design. That is, just have a look at, that is, if the present state is 0 and the next state is 0, for 0 0 condition the required inputs of J and K will be 0x. Okay, x means K can be either 0 or 1. Okay, when it is 0 1, 1x, 1 0, x1, 1 1, x 0. Okay, so this excitation should be known for the design of the circuit. Okay, and this is the design table, that is the detailed excitation table of our circuit. Here the present state. Okay, here this is the present state and this is the next state. So it is an we know that it is an up counter. If the present state is 000, after the first clock pulse the next state will be, we know that it is 001, because it is an up counter. Okay, and if the present state is 001, the next state will be 010. Okay, and if the present state is 010, the next state will be 011. Okay, so likewise we are writing the table, and after at last we know that if the present state is 111, what will be the next state? We know that it will again restart. Okay, that is the next state will be 000. Okay, then after that we have to write the required excitations here. The required excitations are based on the corresponding present and next state Q output. Okay, so for designing the J3 and K3, we have to look the Q3 in the present state, also the Q3 in the next state. Okay, so this first column and this fourth column. Okay, this and this. So based on these values we are writing the excitation values for J3 and K3. Okay, so first value is, that is 0 0. Okay, the Q3. Okay, so 0 means we know that J3 and K3 should be 0x based on the excitation table. Next is also 0 0, so J3 K3 will be 0x, and next one is 0 0, so it will be 0x, and next one is 0 1. Okay, that is present state is 0 and next state is 1. Okay, so 0 for the combination 0 1, we know that the excitation should be 1x. Okay, and next one is 1 1 1 1 means x0. Okay, next 1 1 x0 1 1 x0 1 0, which means the recurrence should be x1. Okay, so likewise we can write this j2 k2 j1 k1 like that. This j2 k2 can be written as, that is by considering q2 in the present state and the q2 in the next state. Okay, for each combination we can write j2 k2, and for each combination of q1 q1 we can write j1 k1. Okay, after that we have to draw the k map for j3 k3 j2 k2 and j1 and k1. And we know that by writing the values of j3. Okay, here we are considering q3 q2 q1 are the variables. q3 q2 q1 are the variables, and first we are going to draw the gamma for j3. Okay, j3. Okay, so for each values, there is for 0 0 0, we know that the value of j3 is 0, so here it will be 0 0 1 0, then x x x x. Okay, so a pair is possible here. Okay, and the expression of that pair is j3 is equal to q2 q1. Okay, like that I can draw the gamma for k3. From that also we know obtain k3 is equal to q2 q1, and j2 we will obtain it as j2 can be q1. Okay, and k2 can be q1. And also we know that here in the case of j1 and k1, the k map is not drawn here. It should be drawn, and we know that by observing these values j1, all there is no zeros here. Okay, there is no zeros in j1 and k1 here. Okay, all are 1 and x. Okay, so we can group it as 8 ones. Okay, all are 1s and x's. Okay, so here it will be no zeros will be there in the k map, so all can be grouped as a 8 ones. Okay, and we know that when 8 ones can be grouped, the value will be, this j1 will be 1, and also this k1 will be 1. Okay, so j1 and j1 will be 1, j1 is equal to 1, and k1 is equal to 1. Okay, j1 is equal to 1 and k1 is equal to 1. Okay, and after that we are going to draw the table, the logic diagram. So here we know that we have to use 3 JK flip-flops, and the input of the first JK flip-flop is 1 1. So here j1 is 1, k1 is 1. Okay, so j1 and k1 are 1, and what about j2? j2 is q1, k2 is q1, so the q1 is given as input to j2 and q2. And what about j3 and k3? j3 is q2 q1. Okay, so here we are taking q1 and q2 from here using an AND gate. We are giving it as the input of j3 and k3. Okay, so there is a 3-bit up counter, and next one is the design of a 3-bit up down counter. That is, both up counting and down counting can be possible using a single circuit. Okay, and we know that using the 3-bit counter we have to use 3 flip-flops, so 0 0 0 2 1 1 1, both in up direction and downward direction. And also for selecting the up and down modes, a control input, that is a mode signal, have to use here. That is capital M. This is the mode signal. That is, which means when M is 1, the counter will counts up. When M is 0, the counter will counts down. Okay, that's the condition we are taking here, and we have to draw the state diagram. State diagram is such that we are starting from 0 0 0. So when M is 1, okay, so this is M, we are writing it is 1. Okay, when M is 1, the next state it will count up, that is next state will be 0 0 1. Okay, and for when M is 1, next state will be 0 1 0, like that it will go like that. And also when M is 0 here, that is the initial state is 0 0 0. When M is 0, the next state will be 1 1 1. Okay, then again when M is 0, the next state will be 1 1 0. It will count back, that is reverse direction. So the state diagram will be like this. And also here we are taking JK flip-flop as our flip-flop, and this is the corresponding present state and next state modes. So here we know that first we are considering present state as 0 0 0. When this mode value is 0, that is it will count downwards, that is the next state will be 1 1 1. Okay, and also for the present state 0 0 0, when the mode value is 1, the next state will be 0 0 1. Okay, and if the present state is 0 0 1, when this mode value is 0, the next state will be, it will count down, that is 0 0 1, it will count down to 0 0 0. And also when the present state is 0 0 1, when the mode value is 1, it will count up, that is 0 1 0. Okay, likewise we can write this table. And also here we are considering these 4 as variables, q3, q2, q1 and m as variable. Okay, and we know that using these 4 variables we can write 0 0 0 0 to 1 1 1 1. Okay, so likewise we can simply write these values from 0 0 0 0 to 1 1 1 1. Okay, it will automatically come like that. That is when mode 0, mode 1, mode 0, mode 1, like that it will automatically come. Okay, so you must write from 0 0 0 0 0 0 0 1 0 1 0 0 1 0 0 0 1 1 0 1 0 0, like that up to 1 1 1 1. Okay, and same as in the previous state, here we have to write the required excitations by considering q3 and q3. Okay, we can write j3 k3 by considering q2 and q2. We can write j2 k2 by considering q1 and q1. We can write j1 and k1. After that we have to draw the k map for j3 k3 and j2 k2, j1 and k1, like that. Okay, and this only 3 k maps here we have shown. By properly arranging the values of j3, we will obtain the expression as j3 as q2 bar q1 bar m bar plus q2 q1 m. Okay, and also k3 as q2 bar q1 bar m bar plus q2 q1 m, and k2 as q1 bar m bar plus q1 m. Okay, and the value of j2. Okay, j2 is same as k2, that is j2 is equal to k2. So from this diagram we know that when so this is the value of mode signal we are using. Okay, mode signal we are using, and j1 and k1, by observing the first j1 and k1 here, no zeros are here, so all these 16 cells will have either the value of 1 or x. Okay, so we can group it as 16 ones, so the output will be what will be the output, j1 is equal to 1 and k1 is equal to 1. Okay, so here j1 is equal to 1 and k1 is equal to 1. Okay, and so here j1 is equal to 1, k1 is equal to 1, and on that we know that j2, what is j2? j2 and k2 will be q1 bar m bar plus q1 m. Okay, so here it is q1 m and here it is q1 bar m bar. It is added using an OR gate and it is given as the input of j2 and q2, like that we obtain the value of j3 and k3. Okay, so this is the circuit for a synchronous 3-bit up or down counter. Okay, so thank you. You must learn the circuits well. Simply we can design any bit counter, that is if it 4-bit counter, 5-bit counter, like that. Thank you.